Hello everyone, I'm Junyang Gao. I will present our work on efficient knowledge graph accuracy evaluation. This work is in collaboration with the product graph group at Amazon. Let's first start with the introduction of the problem. Here is an example of the knowledge graph. Entities are connected by relationships, and the data is typically represented as a subject, predicate, object triple in the knowledge graph. But nowadays, the knowledge graph construction process are far from perfect. So, knowledge graph may contain many incorrect information. Let's define knowledge graph accuracy as the percentage of triples being correct. Here we consider a triple is correct if the corresponding relationship is consistent with the real-life fact. Knowing the accuracy of knowledge graph is important. It provides feedback to the knowledge graph construction process and helps to improve it. On the other hand, downstream applications of the knowledge graph also need to know its accuracy. For example, if we want to use knowledge graph in Google search or personal assistant like Amazon Alexa, the knowledge graph should be highly accurate. Despite its importance, the problem of efficiently and reliably evaluating knowledge graphs has been largely ignored by prior research. Here, we list a few challenges in knowledge graph accuracy evaluation. First, given the median or even billion size knowledge graph, it's infeasible to judge the correctness of every triple. Typically, we can only sample a few and calculate an estimation of the knowledge graph accuracy. Second, as we mentioned earlier, we consider a triple being correct if the relationship is consistent with the real-life fact. This is a very high standard. So the correctness of triples are mostly rely on human judgments, which is time-consuming and very expensive. Third, knowledge graph is evolving over time, as we continuously extract more information and introduce new facts into the graph. So the accuracy evaluation should not be a one-time process. We always want the accuracy of the latest version of the knowledge graph, or even monitor the accuracy over time. Here we consider the evolving KG have insertion-only updates. So our mission is to handle these challenges and propose solutions that enables efficient and quality knowledge graph accuracy evaluation. On the one hand, we want to accelerate the knowledge graph accuracy evaluation process on both static and evolving knowledge graphs. On the other hand, since we sample and estimate, the evaluation result should be statistically meaningful and accurate. The unbiased estimation and user-specified confidence interval or margin of error can together guarantee the quality of a result. Manual annotations is the most important part of the evaluation process. Before we move forward, we show a very important properties of the manual annotation cost, and this observation also motivates our solution. The first question is how to annotate the correctness of a triple. Here we consider a two-step annotation process. First, entity identification. Entities are typically represented as a unique ID in the knowledge graph. It's not human readable. For example, the President Obama in the freebase is represented by this string. Even though we translate the triple into a fact in plain English, the mentions of real-life entities can still be ambiguous. For example, the name Michael Jordan can refer to an actor, the basketball player, or a professor. So, the human annotators must first establish a connection between the ID and the actual entity which it refers to. This step could be complex as it involves searching, validating, and disambiguating among multiple sources and evidence. After the identification step, and we have a clear context of the fact, the second step is relationship validation, which is much cheaper. since we only need to find evidence to check one specific statement. And here we point out the important property of manual annotation cost. Auditing on triples about the same entity can be of lower cost than on triples about different entities. Well, given the two-step annotation process is not hard to explain. First, triples about the same entity can share the entity identification step. Also, annotating triples about the same subject has less context reach and easier to find evidence. Well, experimental results also confirm this property. So we designed two sets of annotation tasks for human annotators and compare the accumulated time usage. The first task randomly chooses 50 triples from 50 different entities, while the second task also randomly chooses 50 triples, but they come from only 11 different entities. Two tasks both have 50 triples, but the second task takes nearly only half of the time than that of the first task. This observation tells us that the number of samples is no longer a good indicator of the annotation cost. When designing evaluation solution, we should be mindful of this actual property of the manual annotation cost. So our solution proposed to apply cluster sampling for knowledge graph accuracy evaluation, where triples from the same entity are joined together. Now here we consider a group of triples with the same subject as a cluster, so-called entity cluster. So we first talk about how to do the evaluation on static knowledge graph. We propose to use two-stage weighted cluster sampling, or TWCS. So the first stage is to do weighted cluster sampling, where each entity cluster is chosen with the probability proportional to its cluster size. Then, the second step is to randomly sample triples from chosen clusters. More specifically, for each sampled cluster, we randomly sample at most m triples for manual annotations. The value of m is chosen by the users. And here is a formula to calculate the unbiased estimation and its corresponding confidence interval. The formula is very simple. The estimated accuracy is just the mean value of the estimated entity cluster's accuracy. And here is how do we calculate the margin of error. And we need to make sure the user specify a certain value of the confidence interval or margin of error, and we need to make sure that this value is no larger than the user set threshold. There are many benefits of the TWCS. First, cluster sampling enables faster manual annotations, as we demonstrated earlier. Also, the second stage sampling caps the total number of sampled triples, since we only choose at most m triples from each cluster for manual annotations. And most importantly, weighted sampling could reduce the variance among accuracies of sampled cluster, and smaller variance leads to fewer samples needed. Here we highlight some experimental results to demonstrate the efficiency and effectiveness of our proposed solution. We compare different sampling strategies: SRS, simple random sampling, which is the common practice for accuracy evaluation; RCS and WCS are random cluster sampling and weighted cluster sampling. The TWCS is the two-stage weighted cluster sampling that we propose to be the best. So we set the same estimation quality threshold, and then we ask human annotators to audit the sample triples and record the total time usage. So as can be seen in the figure in this table, TWCS cut the evaluation time up to 60% compared to the popular simple random sampling, without loss of evaluation quality. We continue this comparison on other knowledge graph. So, for example, on NEL and YAGO. For economy considerations, here for this set of experiments, we replace the actual annotators with an approximate cost function derived from their auditing performance. and we repeat so because this is an approximate cost, so we repeat the sampling procedure, just this random runs under 1,000 random trials, and we report the average with standard deviation. Well, still, TWCS gave us the best result. We also compare the TWCS to state-of-the-art solution called KGEval. Still can be seen in this figure. If we compare the annotation time, it gives us the same quality of the estimation, but in terms of the time, TWCS wins by a large margin. Now we talk about how to do the evaluation on evolving knowledge graph. So the big question is how to incrementally evaluate the accuracy of the updated knowledge graph. We introduced two solutions. First, reservoir-based incremental evaluations. The main idea is to use a weighted variant of reservoir sampling and always maintain a weighted cluster sample on the current knowledge graph. Each new entity in the update has certain probability to replace an old sample in the reservoir. And after this reservoir sampling procedure, the current sample in the reservoir are guaranteed to be a weighted cluster sample in the updated knowledge graph. The reservoir sampling helps us reuse a large portion of the annotated samples from previous round. Well, in this paper, we also shown that there is an upper bound of the number of old samples being replaced, which is actually the incremental cost that we need to pay. Another solution is to use stratified-based incremental evaluation. The main idea is to use stratified sampling to combine estimation results from original knowledge graph and the knowledge graph updates. So for example, let's consider the base knowledge graph and updates as two strata. So we have already drawn samples from the base knowledge graph, and now we only need to draw a few more samples on the update until the overall estimation using stratified sampling is accurate enough. So when more updates coming in, we only need to sample on the new strata without discarding any previously sampled triples. So compared to the reservoir-based solution, stratified-based solution allow us to fully reuse the samples in the previous evaluation without discarding any. So again, these two solutions can both guarantee an unbiased estimation of the knowledge graph accuracy with confidence interval. Now, let's see some experimental results. So we first compare the efficiency between these two incremental solutions. Reservoir-based solution is the red bar, stratified solution is the green bar. Since there's no state-of-the-art baseline for this task, we simply use a very naive baseline solution that restarts the evaluation process from scratch whenever the knowledge graph evolves, shown as the blue bar. So here we consider the scenario that we have already evaluated the base knowledge graph, and then one batch of the update is available. So we vary the update size, and we also vary the update accuracy in these two figures. As can be seen here, well, stratified-based solution is more efficient than reservoir-based solution, since it reuses all the previous efforts we have already done. However, there's also a drawback of the stratified sampling solution keeping all these samples. So for example, if we are in bad luck, then there will be a certain estimation that is way off the ground truth. Though with very low probability, it still could happen in practice. So in this experiment, we try to monitor the knowledge graph accuracy as it evolves through 30 batches of updates. The red line is the ground truth accuracy, and the blue ribbon area is the user-specified margin of error. As shown in the figure, with an initial bad estimation, reservoir-based solution can quickly converge to the ground truth accuracy, as it always updates the reservoir samples as knowledge updates and refresh the reservoir samples as knowledge graph evolves. While stratified-based solution hardly recovers from the best estimation at the beginning, and it keeps all the samples. So So some bad estimations will always influence its subsequent evaluations. So when choosing these two solutions, keep in mind this trade-off between the efficiency and fault tolerance. So fault tolerance. Lastly, a brief summary of the talk today. We consider cluster sampling for efficient knowledge graph accuracy evaluation. Well, cluster sampling can take advantage of the property of the manual annotation cost and rises in practice. And we propose two solutions, reservoir-based and stratified-based, for efficient incremental accuracy evaluation on evolving knowledge graphs. Though in this paper we mainly focus on the text of knowledge graph accuracy evaluation, it's worth mentioning that our proposed sampling techniques are general and can be extended to relational databases if we carefully define the notions of the entities and relationships. Thanks. Thank you.